A little while ago,
Oops!
I made a video where I built an audio frequency visualizer based on the output of a soundbar that I bought. And although that project was a great learning experience for me, the final design that I ended up with really wasn't very good. I kind of just ran into problems and slapped together solutions until I had a convoluted mess that seemed to work. So, I'd like to revisit that project and build something that I think is a lot better. The big problem that I ran into during my last video is that my soundbar had its own volume control built into it, and the volume the soundbar itself was set to affected the sound signal coming off of the output lines that the microcontroller was reading. This meant that if I turned down the audio, the LEDs would stop responding to the music. I didn't like this. Revisiting this project, rather than going online and trying to find a soundbar with a preamp output line, I figured, hey, why not just make my own soundbar? In order to make my own little soundbar, there's actually only a few things that I need. A speaker, a way to take in the audio from my phone, and a way to control the volume. From there, I can just split the audio from my phone so that it is going to both the amplifier for the speakers and the microcontroller for the lights. This way, the volume of the speakers doesn't affect the amplitude of the microcontroller's audio samples. To take in audio from my phone, I have this Drock audio receiver board. This is nice because it can receive audio via a 3.5mm cable or Bluetooth. And these little terminals on the top make it pretty easy for me to use the audio it is receiving for my own purposes. For the speakers, I have this 4-inch pair of tweeters that are rated for 180 watts and have 4 ohms of impedance. I've had these lying around for a while now, so I'm glad to finally use them. If I connect the Drock receiver straight into the speaker will play the audio, even without any other connections or power. It's just quiet. Next, I need to introduce an op-amp so that we can amplify the sound and add volume control. In my previous video, I used a generic op-amp, but this time around I ordered 3 different op-amp ICs that are specifically designed for amplifying audio like this. The first I'm going to show is the LM386. The 386 is an old IC, but it's perfectly fine for small applications and hobby projects like this, because it's simple and cheap. While looking up information on the LM386, I found a video that recommended using this circuit. So this is what I'll be building. The capacitors in this circuit mostly exist to block unwanted frequencies and DC noise from getting to the op-amps and the speakers. Unlike in my last video, I'm not going to be messing around with the gain of the op-amp here. The gain of the 386 is internally set to 20. I could increase it up to 200 by putting capacitors and resistors between pins 1 and 8, but I'm just going to leave it at 20. One video I watched online highlighted this chart on the datasheet. It shows the potential power output of the amp given the power supply voltage and the impedance of the speaker. You can see that with these 4 ohm speakers, we're kind of limited on how much power we can get out of the 386. From 5 volts to 12 volts, the output doesn't change much. But we can at least test it and see how it sounds. After putting together the circuit, we have 3 things to connect to it. The power source, which will be 5 volts for now, the Drock receiver, and the speaker itself. All 3 need to be grounded together. The power source connects here to pin 6. The left or right channel from the Drock receiver will connect here, before the capacitor to pin 3. And lastly, the positive line of the speaker goes here, after pin 5 and a 470 microfarad AC decoupling capacitor. I'm pretty sure this capacitor is here to block any DC voltage from getting to the speakers. For simplicity, I'm just going to use one of the audio channels for now. Once we have these all in the right place and grounded, we can turn on the power and see how it sounds. It's clearly much louder, but it sounds pretty bad. Before trying to address the distortion, let's put in a 10 kilo-ohm potentiometer so that we can control the volume. Rather than trying to use the potentiometer after the amp, we should actually place it before the amp. Also, if you use a regular linear potentiometer, it will sound like this. It's easier to tell in person, but moving the pot even slightly causes it to very quickly go to maximum or 0 volume. It's not a gradual change. In order for the volume control to sound smooth and gradual, I had to go online and order some logarithmic potentiometers, whose resistance changes exponentially rather than linearly. With a logarithmic pot, if I turn the audio down a bit, you can see that the distortion clears up a lot and it actually sounds pretty decent. I think the audio is distorting because the LM386 just can't put out enough power to produce clean audio at higher volumes. If I swap out my 5V supply for 12V, I think it sounds a little better, but it still distorts at higher volume. Remember from earlier that the datasheet showed us that upping the supply voltage for the 386 won't improve the output voltage much. So, I think I'll swap out the LM386 for a higher power amp. The next one I'm going to try is this TDA 2050. While the 386 is rated as maxing out at only around 1 watt, the datasheet for the 2050 says it's rated for up to 50 watts. Comparing these two charts on their datasheets, it seems like with a 5V power source, they may not output very different voltages. I'll supply 12V this time because the TDA 2050 doesn't seem to level off the same way the LM386 does. And hey, that's much better. Or at least I think it sounds better. Not perfect audio quality, but I feel like I can bump up the volume higher before it sounds distorted. I could try higher voltages like 18 or 24 volts to see how that sounds, but I think I'll just stick with 12 for now. I have a third and final amplifier that I will use when I go to higher voltages. Before doing that though, I want to move on to making the spectrum analyzer that will light up with the music. The most important thing that I explained in my last video that I'll quickly summarize is that the analog audio going to the speakers is centered around 0 volts, meaning half of the audio signal is negative. When connecting with one of the pins of the microcontroller that will read the audio levels, you don't want the voltage applied to those pins to ever go negative, because pulling current from the pins while you're trying to read from them will damage them over time. So, we need to bias the voltage up enough that it never dips negative. Using my oscilloscope, I know that the Drock receiver is putting out a signal that is about 2 volts peak to peak when my phone is at maximum volume. So the signal is ranging between -1 and +1 volts. To introduce the necessary bias, we can build a fairly simple voltage divider. The amount of bias we are introducing with this voltage divider is equal to this formula. So, using a 5V power source, because that's what we'll be powering the microcontroller with, I'll choose 100 kiloohms for R1 and 220 kiloohms for R2. This should introduce about 1.5 volts of bias. As I put together the voltage divider, we can actually see the voltage shift up on the oscilloscope. Another important thing to note is that the pins of an ESP32 operate off of 3.3 volts, whereas an Arduino Uno, for example, operates off of 5 volts. This means that any signal going above 3.3 volts isn't just unreadable, but also potentially damaging to the microcontroller. Thankfully, the Drock outputting 2 volts peak to peak means that with a bias of 1.5 volts, our signal should range between about 0.5 volts to 2.5 volts, which is a nice amount of the 3.3 volt range that we have available, while also leaving some wiggle room on both sides. Putting together the bias circuit, and connecting the Drock receiver and a microcontroller to it, I can quickly use an analog read script to see what the ESP32 is reading. Music produces a very messy signal, so I'm just going to play a single tone from a website on my phone. A single tone will produce an easy-to-read sine wave. The tone looks like this on an oscilloscope, and sounds like this. And this is what I can see using the serial plotter on the Arduino IDE. I'm pretty confident the microcontroller is reading what it needs, and I'm not going to damage it now. A thorough explanation of the code I'm going to use would add a lot of time to this video, so I'm going to try to just cover it as briefly as I can. In order to drive the LEDs based on the audio signal, we want to use what's called a Fourier transform. The Fourier transform is a mathematical analysis that will break down the complex sound signal into its various frequencies. Beyond that, the details of the Fourier transform really are not important. I'm just going to summarize it by saying that I'm using the Arduino FFT library for the Fourier transform, and I'm using the Fast LED library to change the colors of these LED grids that I have. To use these grids, you just need to connect them to ground, supply them with 5V power, and connect them to one of the microcontroller's data pins. If you want the code, I'll have it linked down in the description. I now have 2 different devices that want to read my audio signal. The amplifier wants to read the signal straight from the Drock receiver, and the ESP32 wants the signal after it has been biased. This time, I'm going to use both the right and left channels of the Drock receiver by combining them through 1K resistors. That will serve as input to my bias circuit, and I'll run a jumper wire to carry the signal to the amplifier as well. The last and most expensive amplifier IC I bought is this LM3886 amplifier, which has a higher output potential than the other two, and has extra features built into it like a mute pin. I also went ahead and bought a 4-ohm mid-range speaker, woofer, and a crossover to really test the final sound quality of my homemade soundbar. This crossover goes after the amp, and is a collection of low-pass, bandpass, and high-pass filters to filter the sound being passed to the woofer, mid-range, and tweeter. With this, the low frequencies are primarily being passed to the woofer, the midtones are going to the mid-range, and the higher frequencies are going to the tweeter. What this means is that the speakers will put less effort into trying to play sounds that they aren't good at reproducing. So the overall sound quality should be better. I also bought a heatsink for the LM3886 because I wanted to try giving it a higher supply voltage, and these amplifier ICs can generate a lot of heat. Maybe the heatsink wasn't necessary, but I didn't want to burn it out on accident. Also, I bought some of these TLE2426 rail splitter ICs. Using these, I can take the 30-volt DC output of my variable power supply and divide it into a negative 15-volt and positive 15-volt reference voltage for the amplifier. Op-amps need positive and negative voltage references in order to work right. Trying to get decent results when you have no negative voltage is possible, but annoying. These small ICs will allow me to do this. This will be the final circuit that I'm building, putting everything that I've talked about together. Now, I updated the code on my ESP32, soldered the bias and amplifier circuits on prototyping boards, connected the speakers, the crossover, and the LED grid. All I needed now was to connect my 5-volt and 30-volt power sources. And finally, after all this work, I can turn on my power to hear and see the music. I also accomplished my goal of being able to turn up and down the music without affecting what the ESP32 is reading. Not everything here is strictly necessary, but I wanted to do what I could to make the final result something worth building. Here's the different parts highlighted so you can hopefully get a good idea for what is where between the wiring diagram and the actual board I put together. This layout isn't optimized to prevent noise or interference. I just tried to make everything nice and easy to see. Sometimes the audio quality sounds a little tinny to me, but I mostly built all this to experiment and build my own amplifier. If my focus was on getting the best possible sound quality, there's actually a lot I could do differently. To get better audio quality, I could build a proper box for the speakers, buy more expensive speakers, buy a newer and nicer amplifier IC, maybe supply it with a bigger negative and positive voltage range reference, that might help. Laying out the wires differently so they don't cross over each other or run parallel too close to each other could help as well. I could also buy different resistors and capacitors because there are specific ones that are much more suitable for use in an amplifier like this. I just didn't feel like ordering a bunch of specialized parts. I used the cheap ones that I already had. So there's a lot I could do to improve the sound quality, but I accomplished my goals. So I'm happy with what I built. I hope you enjoyed this journey I went on to play around with amplifiers and speakers. I really enjoy messing around with this stuff, even if sometimes I want to rip my hair out because I can't figure out why something isn't working. But I hope you found this interesting and informative. But anyways, if you have any questions, corrections, comments, or advice, I'd love to hear them. I'm by no means an expert at this stuff, I just like teaching myself things and figuring out how stuff works. If you enjoy this kind of content, I do want to keep making stuff like this. The hard part for me is just finding the right idea and motivation for a project. So if you have any ideas, let me know. Thanks for watching.